Hello, welcome everyone to this year's EPFL machine learning course. Please press subscribe and give a like. So my name is Martin and together with Nicolas Flammarion I'm gonna guide you through the lectures of the course this year. And this year many things are a bit different, but also not necessarily worse. We also think that some things we can improve, and we try our best to make all the materials very accessible to you. So there are a lot of you this year. Again, we have about 500 we would expect. I don't know the precise numbers yet, similar as last year. So just we cannot probably serve all the topic needs perfectly. The machine learning has many use cases and many of you come all over campus. So here, just for completeness, I also want to list many other machine learning related courses which are available on campus if you have some more specialized needs. And just for your information, if you want to click on these links, then just download the slides. We will always provide all our slides on the GitHub and also on the course webpage. All right. By the way, the two seminars we have here, they are also open to master students if you're interested. Okay, about this course today, so this is the first video. We will just post 2 videos a week usually, and then we will have also in-person sessions. I will get to that in a minute. So first question you might have is, what's the grading in the course? So that's important to get these 7 credits. If you want to get the credits in our course, you will be graded 40% by 2 projects, and then also there will be just regular on-paper final exam. You will find examples on the webpage. So projects together are 40% and then the exam is 60%. Okay, the format, as I said, will be a little bit different this time. And so the videos of the courses will always be on YouTube. Then we will have a Q&A session on Tuesday, each time at 5 p.m. And then we will have the exercises, which I will explain later. And here you see, if you also go on the webpage, you see that there is the schedule already, what topics we're going to cover in each week. And then you see that I will cover mostly the first 3 or so weeks, and then Nicolas Flammarion will take over, and then in the end I will also cover some parts on unsupervised learning. All right, as we said, the lectures will be recorded this time. Hopefully we can still have a bit of classroom feeling. It's not quite the same, but we will try our best. So also the annotated lecture notes will be available. And yes, that's about the courses. So this will be posted every Tuesday. Then exercises are very important because, yeah, it is hard during COVID times to be at home the whole time and watch videos. So it's important that you kind of break this boring routine from time to time, and hopefully also join us for the live sessions. So we will just follow the regular EPFL schedule. If it's your week, you are more than welcome to join us on campus, so every 3rd week, because we will have our amazing team of assistants being there in person, the 1/3 of them roughly. And then also the other majority, 2/3, will be available on Zoom, where we have the exercise sessions every Thursday. Don't forget to mark this in your calendar. It's very important to get interaction, to ask questions and discuss with your colleagues and so on. The labs will mostly be in Python. You will learn how to get some of the machine learning examples running really hands down, to see how it works and to experience really the theoretical concepts you also learn in the class. So that's important. That you spend also time for these labs. All right, here's the team of our teaching assistants. So you can also reach them by email, and we will also put you in touch, and we're really looking forward to the first session we have this Thursday. Also, for any questions you might have, please always use the Moodle forum. This is the easiest because it will also benefit all the other students, because if you put your question in the Moodle forum, I'm sure many others have a similar question, then we can all benefit from seeing the discussion there and discuss with each other. So please make use of that for anything you want. There is subtopics and so on, and don't hesitate to to use that for all kinds of things. All right, so that is about the exercises, and again I mentioned the Q&A session, which will be about more the lectures, which is on Tuesday 5 p.m. Okay, final thing, the projects. So this is quite special in this course. So the first project is a bit of a warm-up to also get you started in how to do data processing and machine learning on a kind of a toy example, but still a real data set, which is actually coming from particle physics from CERN. And then the second project, which is a bit in the second half of the course, is the more exciting one, where you can really freely choose your topic, as long as you work in a group of 3 students. That holds for both projects. And in the second project, we will offer you to work on any real-world project you want. You can get in touch with any lab on the EPFL campus in any other sciences or topics. It doesn't need to do anything with computer science and so on. It can be really any school you like. Also other universities in, like, for example, UNIL or other academic institutions, to help them with a real data science project and a real data case, to maybe jointly with that lab identify some new applications for machine learning and do some exciting interdisciplinary project. That is the machine learning for science option, which is about half the students normally choose that. I'm gonna talk a bit more about this later today. We also have other options you can choose. You can also choose one of the 3 predefined challenges we have, which is a bit like a Kaggle challenge, if you know that, which is online kind of competition to let teams participate on the same data set to see who gets the best accuracy from a machine learning system, which is also very cool because you can see your progress and you can see how well your system is doing and how all the things come together end to end when you work with your real data set. Last but not least, we will offer you, for those who are more interested in, for example, research aspects in machine learning itself, we will offer the Machine Learning Reproducibility Challenge, which is a very important project which is offered around the globe, which allows anybody to reproduce scientific results from recent papers to see if their experiments actually make sense and can be reproduced. It's very important, and it's also a good learning experience to actually see what are the newest developments and to start playing with some very new methods coming from the machine learning field. That is the 3 options you have for project 2, and to learn more about this, stay tuned, and also please have a look at the project descriptions and also the course info sheet, which is a PDF available on our GitHub and also on the webpage. So please be careful to read through the modalities, then I don't need to spend too much time on this now in the video. So we will give you an overview in this course. It's not going to cover everything, but we want to give you a basic understanding and also to teach a bit about the fundamentals of machine learning, that it's not just pressing a few buttons in a commercial software or so on, but to try to understand really what is happening, what can go wrong in machine learning, and what can go right, to tell you a bit about the mathematical foundations of it. Well, we cannot go so deep as, for example, in a learning theory course, but we will make sure to cover the basics here. On the other hand, we also want to make sure we stay connected to the real world to actually make you experience the pros and cons of all these methods and aspects on a real data set in a practical application. And this we will also see several times. So I hope we kind of can strike a balance between teaching you practical experience, but also the theoretical foundation. Okay, you will of course not get everything from this course alone. Also see again there's these other courses if you need to have something more specialized in addition to this. So this is just one foundation. And also there are of course many practical hacks going on, which is interesting to see, and also hopefully after our course you will at least be able to understand better what is happening, what are the newest trends and to be able to quickly dive into recent developments if you want to then get more specialized in something. And yes. Okay, so we talked about who are we from the teacher side, but also who are you. This is the course from last year. Actually, I just want to put this here that this is something I really like about this course, that it's so diverse, that this course brings together so many students from the campus, but in terms of numbers, but also in terms of background. So that's really cool that you come from all the schools. Like we have a lot of students from biology, from math, from physics, from life science, mathematical engineering, financial math and everything, and a lot of PhD students. So this is really cool. This makes the course very interdisciplinary, and that's actually a key asset as well if you then work in the teams. So for your projects, I think it's a very good and strong suggestion to work in an interdisciplinary team, that if you just don't team up with the same people as usual, which have the same background as you, but team up with someone from a different background, so you will be more successful on the project too, because these projects, especially the machine learning for science, are really about combining different skills. So if, for example, if you can bring together someone who's good at programming, if you can bring that together with someone who's good at math and someone who is good at the domain application, for example, biology, so this can really give some really stronger teams. And also we think machine learning is an interdisciplinary topic if you apply it. So this is a good opportunity for projects, and in the forum on Moodle it's very easy to find your teammates, and even now with the COVID situation it's even easier to actually work together remotely anyway. So this is a good opportunity. So welcome everyone. And yeah, the performance of all these students from all these different schools is very impressive in the last years, and also not what you would usually expect from naively thinking about the topic. So it's not necessarily a CS course, but everyone here is super welcome and successful. Okay, this is a small tool we have as an additional learning experience. So this is not a replacement for the exercises and lecture materials. This is an addition to remind you about the keywords we have in the course. This is a nice phone app, but you can also use it in the browser, which reminds you on the Wikipedia concepts which relate to this course. And it's actually quite a nice learning app, which also has a small machine learning component to actually remind you of those errors you make, to remind you again after a certain time to adapt to how fast you're forgetting and learning. So very nice relation here between human learning and machine learning. So if you want to give that a try, you're welcome. This is this Gamified learning app. Okay, let's get to the content. What is machine learning? For me, it's basically, I would just describe it as algorithms which are defined also from data, or which learn from data. So instead of just hard coding an algorithm line by line in code, you would also have that algorithm is determined by some data set. So that means it's parameterized by some numerical values, and these values are, you can think of them as little knobs, the weights of this system, and these knobs are learned, and that just means that they're optimized so that to best fit the data set. And what these knobs are, that really depends on what kind of machine learning model we are using. So it's one case for example, linear regression models. It's a same idea for neural networks, for example, or any other machine learning model. The idea is that it adapts to the data and then can be used as an algorithm, for example. Okay, let's give a concrete example. Classification of images has been used a lot in the last 10 years, has become a classic application for machine learning. Just want to give you a nice mathematical algorithm which can do that. And here's the picture how this works. So you need to to represent your data points, which you have on the bottom here. So this is your training data. You have 6 images. So look at one training data point. You need to represent that as a point in the feature space. So you need to represent that image as a point, which then allows us to do a machine learning model to separate these points from the other points. For example, from the dog images, to separate them from the cat images. What do I mean by separate? For example, here we take a simple model. That means we just take a plane or a line here. So if you're in 2 dimensions, you would just say every point here is a point in the plane. You would look for the best line to separate these 2 groups of points. If you can separate them like here, then you would say I have found a good classifier. So now if you have found this classifier, which is the line, then you can take a new image. So this image here is an image for which I don't know the label. I don't know if it's cat or dog. And then I can just use my machine learning system to answer this question, and it would just say, oh, it's lying on which of the 2 sides? It's actually lying on the blue side. Therefore, the answer of the system will be that this is an image of a dog. That's how a classifier works. Now, how is an image actually a 2-dimensional point? Not really. So data points in machine learning are usually more than 2-dimensional. They have many features. Here the features are not only 2 of them, but there's for example hundreds of features, which are the pixels, the values of each pixel. You can just write them all in a very big long vector. So if the pixel is black, you write 0, and if it's white, you write 1, or the other way around. So you have this image here, which is maybe, I don't know, 100 pixel or 1000. What that means is that the point which represents the photo is a 1000-dimensional data point of 0s and 1s. Or you can also have gray for each pixel. Then you have each value goes between 0 and 1, can be any number or percentage. And so this is just a naive way to represent data in a numerical format to get, or the actual term for this is to find features for the original item you have, which here is a digital image. So once you have transformed it into features, that means that we have a point in d dimensions. That means we have found d numerical features to represent our point, and then we can do machine learning with that. So that's how this works. And how was the learning done? So how do you actually find this plane, separating them? So I mean, in d dimensions, it's not going to be a line. That's going to be a plane. So also a so-called hyperplane, which you're trying to use and trying to find it such that it has the red points on one side and the blue side points on the other side. How do you do this? How does this training work? Here's a very nice algorithm which is actually still super fundamental, and it's actually still the same algorithm is even used now to train neural networks. Basically, there has been no new algorithm which was better than this. Basically, I mean, this is just a very simple example of the algorithm, but the algorithm comes actually from 1957 already, where it was applied to this case of linear and actually then also more powerful nonlinear classifiers. So how does it work? So our model is this plane here, which is the black hyperplane. So how do we describe planes? We describe them by a normal vector, for example, and let's say we only interested in planes which go through the origin. So this is a bad plane, and it's described by this weight vector w. That's just a normal vector being orthogonal to the plane. W has d entries, it's a d-dimensional vector. So this is a bad one. How do I find a better one? I want to improve my plane. So what I do is I find a point which is misclassified, which is on the wrong side. So this guy here is a red data point. That means it's the image of a cat, for example. So that's so far so good, but the problem is it's lying on the bottom side of the plane, so it's lying on the blue side, which it should not. So we want that all the red points are lying on the upper side. So what we do is it's funny, there's not so many things you can do if you're in extremely high dimensional space. So remember, the point x is a super high dimensional vector, for example, 1,000 dimensions, 1,000 entries, because it's from this photo. Same for w. W has 1,000 entries, so I don't want to talk about crazy operations in such a space. But what I can definitely do is the simplest thing I can do is add a little bit of these vectors to each other. So I take the wrongly classified data point, I add it a little bit to the end point of my w. So by a little bit, I just mean I take the vector and maybe multiply it by 0.1. So then I get this vector here, and that is my new normal vector w. That's what I'm going to use as my new plane. So nothing magic has happened here except the old plane, we had it. We modified it by adding a little bit of one wrongly classified data point. Now we have a new plane. That's one of the iterations of this algorithm. And you can see the plane has already become better. So now we separate almost all the points of the two kinds or classes. There's still two which are wrong, but all the red ones we got correct already. So that's how you would perform an iteration of this algorithm. This algorithm is actually called stochastic gradient descent nowadays. So this is just a very simple example of it for one particular model and loss function. So we will get to what this actually means. But the algorithm here is this is what we did, and this is also known as the support vector machine nowadays. So we will actually talk more about this type of method in the middle of the course. And the nice thing about this algorithm is that it's super fast, right? So to perform this one iteration, of course, I have to do several iterations in the end, but per iteration, I only need to add two vectors to each other, which is extremely cheap. It just costs me 1,000 floating point operations to add these two vectors and maybe multiply by a scalar. So this is the type of operations you should think of when we do machine learning. So we have inner product, which was happening to see on which side does our point lie. And then we have the addition of two vectors. This is what we used for the algorithm, and this is scalar 0.1. It's also used as a step size. We will explain later what this means. So this is another example of very typical iterations or operations that are used in machine learning algorithms. And this algorithm here is basically the only machine learning algorithm there is in the world, except that we will explain a bit more and make it a bit more general later on, and see how this can actually be used for many use cases like supervised and unsupervised learning. Okay, but this is the type of method. Why am I showing you this slide? This is what's happening if a machine learning system is trained on hardware. Then you can imagine that the CPU or the graphics card, that's the type of operations they are doing. So they have to compute inner products, which will actually lead to a gradient. We will get to this later. And then they have to do updates on very large vectors. So modern machine learning models, they're not only 1,000 dimensional, but they can have really millions or billions of parameters, often much more parameters than you have data points. That's also something we're gonna discuss a bit more later. Okay, this was one concrete example to motivate you a little bit. And to take this a bit more general, so what has happened here is that we had training data. That was the images of cats and dogs, for example. And they had a label already. The label is which class is it? Is it a cat? Is it a dog? So you have many examples of your task that you want to do. The task is to classify between the two, and you have human annotations of this data already. So that's the assumption we have in standard supervised learning. And this is not always easy. This is actually, very often, this is the main problem here. The problem is not write this one line of Python to train the neural network on this data. The problem very often is to actually even identify this data or find the data or then convince many people to actually do this manual work of labeling to produce the training data for a machine learning algorithm. And then the algorithm we had, so for example, in this in the slide before, I showed you the support vector machine as an example, and we saw that it can be trained by gradient descent. We will make this much more precise later, but there are of course also other machine learning methods. In any case, they will output a trained model, which we usually call W. So in our case, this was the vector which described the plane, right? If that's going to describe your entire machine learning system. This plane is the entire model, is the classifier. If you have that, you can deliver it to your customer, and they are going to use this plane, hyperplane, to decide yes or no, or it's going to be deciding if the self-driving car is going to stop or accelerate. That's also a classification problem. When you have the model, you feed it test data, and so that was the green point I described. And the point there is that you don't know the label, right? So, but you can feed it into your model. Then you ask on which side of the hyperplane is it lying, and you will get an answer. Either it's a dog or it's a cat. And then you will also want to have a very solid evaluation. That's an important topic. So we will not be comfortable with deploying such a machine learning system if we do not have thoroughly evaluated it. So, and this is also something we're going to discuss. So if someone else gives you a trained model, how do you decide that this is a well-trained model? How are you sure that this is accurate enough? But that's the scheme of like supervised learning, and then later in the course we will also talk a bit more about unsupervised learning, which is a different and actually even arguably more interesting use case where you try to do learning if you do not have manually labeled training data, and sometimes you can also use some auxiliary tasks or train something on itself to also learn something about your data. So we will get to that in the second part of the course. Okay, so let's take a step back. So what does this whole thing have to do with intelligence? So far it didn't seem very intelligent. We just fitted a linear plane, and that's true. So actually you can say that machine learning is just a regression, and that's actually quite an accurate description. But nevertheless, it is a big step forward in this context compared to traditional models, where we only had hard-coded rules, which were, for example, by a human, which was programming, for example, a hard-coded chatbot. So if the user says this, then the chatbot answers that, and that is far away from the type of accuracy and kind of quality you can get with modern machine learning models, which are of course not intelligence yet, but it's trying to make a step towards being better at like generalizing and really understanding some aspects of these tasks. But at the core, these models are really just regression models as we described. So another view on this is if you compare this to neuroscience, for example, what is the difference? So, I mean, neuroscience is trying to understand biological neural networks. How do they work? Why does a biological brain work? This is a super interesting field, of course, on itself, and it's basically independent of machine learning. Machine learning, on the other hand, is also independent of this. It's just trying to see, it's kind of an engineering approach. Can we just build a machine that flies? It doesn't need to resemble a bird. We just want to build some whatever machine. In the case I showed you, we built a plane, not a flying plane, but a linear hyperplane. Doesn't have anything to do with whatever smart brain or so, but but it works if it's trained on enough data for some applications. So that's the other approach, and then machine learning would not care if the models they come up have any similarity to a biological brain, but you just care that you get a good test accuracy on this class, or that you can have a good test accuracy to drive your self-driving car. So far they seem completely separate, but what is actually also interesting is that many of the models which we get in machine learning, which perform best, which are also related to our artificial neural networks, turns out, but they just came out because they, from an engineering perspective, they turned out to work best. Many of these models also have a similarity with biological networks. So this is a intriguing parallels are happening there. There's still huge discrepancies. For example, in machine learning models, we have every neural network we use here, the artificial ones, they're trained with back propagation. We will explain what that is. That is something we do not really have in a biological brain, that the signal goes sequentially all the way forward from input to output, and then backward again sequentially from the output to the input to adjust the weights. You would not think that in the biological brain you have such a nice and sequential top coordinated and organized process to do this. So the question is a bit, are there actually similar algorithms or not? So this is a huge open question, so we are not going to get close to answering this, but if you're interested in these type of analogies or what are kind of interesting relationships between these two fields, then there are also some other interesting courses, and some are in the neuroscience department. Okay, and another small slide, you've probably seen this already, I will not spend too much time, that just on how does machine learning actually fit with other fields. Everyone has known that the statistics has been around for hundreds of years, and the same computer science a bit less than hundreds of years. But so how do we position this? So we would think that machine learning is actually always a bit in the intersection of all these three things, which is computer science to really have the engineering aspect to make it work, to actually implement it on large data sets, and then the application domain, that there is a clear task that we want to address. For example, we want to classify disease or so based on the genome or so on, where the data comes from and where the answer and training data come from. So if you manage to take this, combine it with such a modeling decision, we said, okay, we can do a linear model, for example, with a plane, and then use a training algorithm from computer science to actually find the best plane efficiently. Then you're in the intersection of all these three things, and then you are in the machine learning domain. Similarly, in the job market, maybe, so you see that these type of skills are becoming more demanded and also actually more frequent. So, I mean, many industry applications nowadays also try to benefit from data, and if you do that, the machine learning is often an important tool. And then you can also see that this is something which of course is working closely together with data science specialists. All right, there's been a bit of a hype in machine learning, or also of course increased interest. And here I just want to show that this has been changed into, this is like the last 5 years. You can see that there's a good increase in interest. So this is from Google Trends. But then also it has flattened a bit, but still there's a high interest in machine learning. And for example, if you compare this to traditional fields like linear algebra, I mean, why do I put these two? It's a bit strange. But the funny thing here is that both these techniques are kind of a bit similar in the way they are used, right? Because also linear algebra is also used everywhere in any application domain. It could be in biology and psychology and geography. Many sciences and also industry applications need this type of data techniques, which have been around for a long time. And then to some degree, machine learning is also kind of the same as linear algebra. It's also just a rebranding of many terms we already had. But one big difference is that now we are actually able to apply it more broadly. We have found more applications, and there is more opportunity to do these data-driven techniques, and also the techniques have improved as well to a certain degree. We'll get to that. The hype can be a pro and con. So you see, if, like maybe 2 years ago, machine learning was really, if you ask people in the industry, on the top of this hype curve. Now it's moving a bit to the more reasonable territory again. If you think that in the very long term things should converge to a reasonable level, then that's the kind of consolidation we are seeing now, that it's not the coolest, fanciest thing anymore, but it's also getting people get a bit more substantial and solid about it, and it's not just enough to just throw the buzzword of machine learning around and that will give you the job there, but it's really becoming a standard tool that many people know about, so that then it becomes also a bit more important to know a bit more details about it and go a bit deeper. So what exactly machine learning, in which sense, for what, and how exactly. So which you can also see that many of the specialized applications like on-device AI and explainable AI, natural language processing, automatic machine learning, there's so many aspects to it. Some of them we will touch in our course, some we will not. Deep learning, of course, graph analytics, there's many aspects of it. And it's nice actually to see that people get more serious about it and do not just use it as a buzzword. Okay, so why do we use machine learning? I hope I have motivated you already a little bit, but I will go quickly to these slides. One thing I really want to point out, that this is not just about the digital usual companies like internet data. So this is really having lots of opportunities in domains which are not traditionally digital. So for example, you see many startups also in this area here, the west of Switzerland, using it, for example, for agriculture to make smart robots, or to have satellite data and make predictions based on satellite data, how to do better agriculture, or NGOs, or for example, bike sharing. Not the best example here nowadays, but maybe they could use machine learning. So I'm just saying this is lots of applications which you would not immediately think of. So people always just think of the internet. But I also want to mention sciences. So this is something we're going to touch when we talk about the project 2, which you can choose. If you want to do machine learning for science, then you can really choose one of these real projects and to identify some new opportunities to actually find a real data set and apply the machine learning tools you learn in this course, apply them to really make an improvement in such an application domain, which is something really exciting, because scientific data is extremely rich and has been traditionally very well collected, and it's exploding in amount and opportunities at the moment. So this is an exciting application, and I believe this also motivates several of you from the other sections on campus to come to this course. And I would just say you're really welcome here, and you, by being interdisciplinary, by being willing to bridge both computer science and your application domain, you're in a very good position. This gives you a unique opportunity, I think. So this is very nice. Okay, but then let's not overrate things. So machine learning is actually just a tiny element in a big system. For example, if you would deploy something like this on the real world, because if you, for example, build a product like for example, have a recommender system on, if you're like TikTok videos or something, it's hard, right? It's not just training a hyperplane, right? Because let's say you get some data from the world, you have to process it, you clean it and so on, and then you look at it and try to decide what you want to do with it. You train a machine learning model, and then you deploy it in your phone app, and then you actually change the whole app by doing this. So now the data collection will be completely different. So you have this kind of feedback loop going on, that if this is the case, this makes it quite difficult to actually then still be sure and measure if you have improved your system or just some other feedback loop or coincidences happened. I'm just saying the real world use cases are very interesting and not trivial, and of course it's not everything here which we'll be able to cover in this course, so you will need to look more in depth if you're interested in some of these aspects. All right. Of course, machine learning is not new, so this is 150 years ago. Maybe some of you have seen this plot. So this is, I should have hidden the term here. So people just collected a lot of data points here. Only the red points were available. And these were actually cases of this a disease outbreak in London. And nobody had an idea what this disease was and how it's transmitted. So it has an uncomfortable vibe now with the COVID. But even then, people try to use data to make sense of what is happening. So we observe all these disease cases, and we don't know what's happening and why people got it and what's going on. So what happened here is that when they looked at this map, which is the data science approach to just plot everything and look at clusters, do some extra exploratory data analysis, for example, they observed that there are some clusters happening. There's a lot of cases around this broad street here or some other streets here. So by this, they figured out that points are clustered around water fountains, and by this data approach, they were able to then come to the insight that this disease is spread from water fountains, which was true, but which was very hard if you have no idea about how this is happening. And this was a very interesting and actually very successful application of data science more than 150 years ago, and maybe now repeating very, very similarly with this COVID app, for example, which I hope many of you are using. It's not machine learning, but it's an amazing app which also tries to collect data while minimizing privacy, which is another topic which is super important for machine learning, which I'm going to get back later again. Yeah, getting a bit off topic, so just want to say that there's been a lot of the fundamentals actually come from the 50s and 60s, so about 50 years ago, including neural networks. And also, you might have heard of the interesting use case, the Turing test, which just to ask if a chatbot has some real intelligence. The way it does this is just by having a black box communicating with a human and then seeing if you can make the user believe that this is actually human. So this is something which is again active, very active now, because a lot of progress in machine learning nowadays is happening in natural language processing, just to produce text and continue conversations. So you have a few words already, you need to provide the next new word to just continue the text all the time. That's how the best conversation and text bot systems nowadays work. And it's a very interesting time nowadays because they being trained on all the text in the world without the need of any manual labels. You just try to train yourself on continuing all the existing text. This is how we get some really impressive results in text nowadays. And we will also touch a little bit more later in the course on this. So then if you had all of this already 50 years ago, so then what's actually new? So what's definitely new is the scale of compute we have available. So computers have become so much faster. It's not only like 10x or something, but it's really you can see here it's like 15 orders of magnitudes which have been improved in speed, how many operations per second can be done, even if many of the models themselves, like neural networks, we have seen that the perceptron I showed you at the very beginning with cats and dogs, that was the first neural networks from actually 58, where that very similar networks are still used nowadays, but just on a larger scale with much more interesting data sets, a little bit improved architectures as well, and with a lot more compute. So the funny thing is that the networks themselves, the people in 1958 were very much equally excited as today about their abilities. So this is the New York Times long time ago about this, actually the perceptron we just discussed. And then the same newspaper just like 3 years ago had this article about, I think this was maybe Google, which trained a very large neural network on images from YouTube actually. And the funny thing is that was a standard neural network kind of, but he used 16,000 computers. And one interesting thing was also that he was trained unsupervised without human labels, but otherwise very much similar architectures, but much more compute, and then impressive gain in quality of these systems, which is valuable. Okay, that's the good side. The bad side is that there is a bit of a hype, but maybe, as we discussed, this is already improving. So what is far less clear is how to deal with ethics in these systems. Also, just even take simpler things like the data ownership, for example. So, if all this data is collected from us, could we please also have the opportunity to actually control or keep our data and decide ourselves which machine learning systems do we want to participate and what do we get in return for providing data. That's a very active research topic I'm also very interested in. Fairness is a bit similar, and then just data ethics is a very big topic which still has many open questions. What do I mean by that? For example, it's quite subtle, right? So usually you think, okay, recommender systems are fine, it's cool, makes me have more convenient shopping, so I can also get these relevant items, whatever I buy on Amazon. So doing these sports items here, so what other items could I be interested in? And then suddenly you can get a bit funny results here. So customers who bought this were also interested in this stuff, which is like pepper sprays and face masks. So you can see that there is privacy, or what shall we say, there is a very strong society implications of these systems. And here you can see some of the interesting conflicts happening. For example, also who should get access to what data, and it's very subtle sometimes how easily you think it's not so sensitive what I browse on the internet. Sometimes what you browse can be extremely sensitive, revealing various interesting things about yourself. So another issue is the lack of interpretability. So we have amazing accuracy in many of these machine learning systems, and particular neural networks. We do not have perfect interpretability, like the network said this is a cat, but it was actually a dog. So why did he do the mistake? So actually, it's a bit similar with humans. Humans also, if a human does a mistake, you also don't have perfect interpretability. Why did this happen, and how did the human make the decision, no matter right or wrong? So, but this is something which is an issue also in terms of accountability, right? If your self-driving car crashes into the wall, as has happened, right, then who is responsible? And so is it the software vendor's fault, or the driver's, so-called driver's fault, or who is at the responsibility there? And also in the medical domain, it's very important. If we trust these systems, we also would like to understand better how confident they are, how sure they are on each decision, and what kind of mistakes they make and why. So this is a very open topic which is far from resolved. Finally, just on a broader scale, there is a lot of interesting questions with society itself, and also, for example, what actually is intelligence. That's a very interesting question on itself. So we are far from that stage, as you will see later in the course, if you can prepare for some underwhelm your expectations. But it's actually, I think the question of what is intelligence is of course super interesting, and machine learning is helping maybe to get one small alternative perspective on this, but of course it's not gonna directly provide a superhuman level of intelligence, but we don't even exactly know what intelligence is, so you also have to be careful what we mean by that. So there is a very different notion of very narrow intelligence. So for example, how many phone numbers in a phone book can you memorize? So there's some tasks which are very narrow, which a computer is better than a human, but there is a huge improvement that humans have over these machine learning models when it comes to generalizing ability. So where the artificial systems are very narrow, they can only do exactly one precise thing. Humans are extremely broad and general in their skills. So if I have been trained to catch a volleyball or something, then later, if I've never seen that, but if somebody throws a basketball at me and I have no idea what to do, I still react roughly correct. Not perfect, but people will do something okay on tasks which they have never seen before. So they have the ability to transfer knowledge very broadly between different tasks, and this is called a generalization ability or transfer learning, which is a very interesting topic which you do not see very much yet in the artificial systems, but people are trying to get more of this, for example, in the NLP domain and many other domains. So that's an interesting area to watch. Okay, and also super important is that we keep these methods reproducible and scientifically documented, and also open source, which is nice. So that is also has contributed a lot to the speed of advancement of the field, that actually people were actually able to measure and compare these different systems on the same task. For example, the data sets themselves are hugely important. For example, the ImageNet data set has contributed so much to the progress of machine learning. Not so much because people have found new neural networks, but because people actually now had an amazingly rich data set, which was standardized enough so that people can compare different systems in a fair way, and then measure progress and make it reproducible. And so that is important, but then also it has the opposite effect that people do then use these few datasets way too much, and then that also contributes on the negative side to the machine learning models are not very generalizable to different tasks. You can only do this ImageNet classification. There are 200 different kinds of dogs, but these models cannot do anything else. That's also a bit of a side effect, that we are driven by very few extremely highly used data sets. So we should try to broaden this to more open data sets and more broader tasks. Okay, before we finish this intro, I have a few examples which your colleagues did last year. This is very cool. For example, this machine learning for science projects. I just want to show you that it's very surprising how rich, how diverse the applications can be of these basic machine learning systems, if you just if you take the time to identify the right opportunity and the right data set and the right application. That's actually the exciting part. The exciting part is not to write the one line of Python to train the regression model. The exciting part is to identify the opportunity. Here is a data set which I could maybe learn something, and then this way I can do it. I could label it this way and then train the model on it to achieve something practically relevant. You can see people have worked on invisibility cloaks. People have, your colleagues have done a prediction on from satellite images where in Switzerland or anywhere can you put a solar arrays most efficiently. Working on bacteria and human stress and toxicological data and material science, gene expressions, product life cycles, as Twitter discussions. It's just huge amounts of different applications which are very nice and very cool that these tools are applicable so broadly. Also, massive online courses analyze the progress of students and stuff. Okay, that's cool. Hopefully we'll get many of these again this year, and you will find more info on the webpage. Okay, just a very brief overview that what can be done in terms of data domains we have. I mean, this is not much new for you. We know that images can be represented in digital domain very easily. Just saying that this has very nice applications in astronomy and biology, both 2D and 3D images, and things like robots which have guided by vision systems. This is an interesting application domain. For example, telling how old people are from just their photograph. That there's lots of fun and not so fun applications. Text is very important. So the main question in text is again, how do you translate it into features? So we'll get a little bit to that. A lot of progress has happened in text domain. It's very fascinating because so much text is actually available already in digital form. So we can try to build better machine learning models based on this data. Has lots of applications. For example, medical text is quite interesting, and machine translation has made amazing progress in recent years, which is also a really cool thing and also one of the nice applications. What you see in the image here is tweets, and they are classified by a system according to their sentiment, positive or negative. There was a game show, but it's already a few years old, and systems have improved a lot since then. Okay, genetic data and medical data in general is super interesting. In the genetics case, it's also a bit like a text. You just have only 4 different letters. So this again is we call this sequence data, right? When you have a sequence of letters like text. The thing is, the variable length aspect is interesting, and also in this case also it's extremely high dimensional. So one biological sample has like millions or many millions of these genetic letters. So usually they just identify a particular set of like 1 million positions, and then so you have 1 million features, and you have 100 people of data points. So this is another interesting use case when you have much more features than you have data points. So what you can do is a PCA, for example, and then it's quite interesting, again relating a bit to this medical application in London with a geographic outbreak. Well, this is something completely different. This again is an example of completely unsupervised data analysis. You just do principal component analysis of your 5 million dimensional data points. You look at the first 2 principal components, and strangely they do reflect a bit of geography. This is what is it showing? Not much, but it's showing that there is interesting patterns in data, and especially that high dimensional data can have very interesting properties. So there is potential to use machine learning on very high dimensional data. And yeah, the availability of genetic data is maybe the most interesting thing, that it has become available much more quick than Moore's law of compute power has improved. So here you see the cost going down exponentially. This is on a log scale, or super exponentially. Another funny domain is audio. So of course it's easy to represent audio data in digital form. Can be interesting for speech recognition. It's a classic use case. There are other also cool applications are when you're trying to bridge two modalities, for example, video and audio. And one thing here, example is just as a funny example is lip reading. So that's another clever use case that people have found an opportunity where there's a lot of data sets available on any video in the world has somebody speaking, somebody moving their lips, and also there is audio next to it. So now you can, let's say, can we actually predict the audio just from the picture alone? Well, from the lips alone, can you predict the sound? And that's what people can do it sometimes, but it's extremely difficult. But because you have so much data, it was actually possible to train a machine learning system to do that, which is then based on a convolutional neural network. But again, the smart thing is to identify the training opportunity, that there is the output already there, and from it I can learn a mapping from image to sound, for example. There is also sound style transfer, which is kind of interesting. So it is possible using neural networks to separate kind of the style and the content of an image, but also of a sound. And then you say, okay, I want to keep the content but change the style. So then it's possible to take someone's voice and translate it to the style of someone else, which can have some risky implications as well, which is also a big discussion on fake generated audio and fake generated images, which is also interesting, and we will touch maybe a little bit later in the course when we talk about generative models, which are models which can, for example, generate fake data in many data modalities such as audio and video, for example. Numerical data is super interesting, for example, in also personal devices, like your heartbeat is recorded in all these fitness trackers, so that's an interesting, very long-term data set. In weather forecast, you have very high time resolution data sets, so it's very interesting to look at data sets which have both a time component and maybe another component like a image component or audio component. So that also gives a lot of interesting applications for machine learning. So you can see I'm quite motivated by the data itself, because that is a source of opportunities. Another one, speaking of this, is simulations, which are very interesting because they can actually be used to generate training data. So for example, if you have a physics simulator, then you can use this simulator to tell a virtual agent to make it experience the good and bad actions, right? And this, if the simulator is fast, can lead to huge amounts of training data, which then can be used to, if the agent has its own small machine learning system, it can use that to learn, and to learn very quickly with lots and lots of feedback. So this is happening in games, and not only for the purpose of games, but for the purpose of finding more and more rich training data for such agents. So this is a very interesting domain where we see a lot of progress as well in recent years. And the internet data, that's the classic boring use case, but well, it's not so boring because it's actually very rich as well. Also public internet data. Okay, and to find more opportunities, that will be your turn. But first we will make it a bit more concrete and move to the actual contents here. So I'm also trying to fix this problem with the bar above, and now let's move to the actual materials. We're done in the intro, luckily. Okay, by the way, all the materials you can always find on the webpage and also on the GitHub. On the GitHub you will find both this version of the slides, but also the annotated version, so I'm trying to make some notes sometimes so you can see. All right, you ready to dive into the math? There is a little bit of mathematics, sorry for that. not so much in this slide, but then maybe in the next one. So machine learning is actually just regression, if you want a very simplified view of it. So we definitely need to understand what regression is. And many of you do already. So because many of you have already taken an introductory course to machine learning. And of course you have taken a basic linear algebra or very basic first year math courses where you know what a regression model is. But here stay with me because we will take a bit of different perspective. All right, so regression, I just want to do this to actually fix the terminology as well. So what we want to do is we have input variables and output variables, and I just want to make sure we're on the same page here. So we have some input, we want to predict some output. So this is probably a bit boring, but it will not take long. So if I visualize maybe the output on my y-axis here, then I have some output variables. So the output variable is usually called y, and that is a number. So it's a real number, for example. And then I have my input variables, which I visualize on the x-axis. So x. And this input x it can be one number, but it's much more interesting if it's many numbers. So it's a d-dimensional vector. That's what we want to do. And this is what we are going to do in all the machine learning applications. So here is your one data point, x. It has an observed value, y. And you don't own, so we also index our data points. We don't only have one data point, we have n data points. So that's what we have in our scenario here. The data is collected. We need the right notation here. So sorry, trying to get familiar again with this iPad thing. So we have many data points, right? Maybe they look like this. So for each of these x data points, you have a corresponding y value. So we need to be careful to really describe this data set correctly, and we will describe it as a data matrix. It's a set of points, and namely the xn points are the input or input variables for each n, and then each point comes with the output value, which is just one number, real number. Can also be a categorical number. If you have the cats and dogs, maybe you have -1 for cats and 1 for dogs. Very important that the xn is d-dimensional. So that's our points, and the n ranges from 1 to capital N, for example. Okay, so now we're good. Now we described our data set. So here is my yn point. Here is my xn point. Okay, why is this important? Because this will always be like this when we feed it to our real application. For example, if you want to give this to Python, then you need to agree how you represent your data matrix. And the notation we're going to use is going to be this one. So for example, in every row here of this matrix, I will collect one of my data points. Let's look at the middle one here. Here is my data point small n. That data point has a bunch of features. So they are called xn, but that's actually a vector. xn1 is the first entry, xn2 up to xn d. So I have capital D entries. I have D features in each of my vectors. So that's what one row here is. And then you have the same. So you have n data points or rows. You have D columns or features. And then here you have one more column, which is the label or the target variable. So this goes up to capital N. Sorry for my terrible writing. Does that make sense? I hope so. Okay, so why do we do regression? It has several purposes. So it's in any case, it's going to be to understand the relationship between input and output, and also to just predict the output. So these are kind of the two most common use cases you can have. So either you just say, okay, I just want to be accurate. I just want to get good prediction for any y when I don't know my label. So that's the task of predicting. And so you just use this training data to predict. The other use cases you want to understand. So you also use the same regression model to better understand if there is a relationship between x and y and what this relationship is. Let's look at a few examples. For example, this is a super baby data set here. For example, we have the weight of a person and the height on the x-axis. So, and we have lots and lots of data points. So what we do is we fit a regression model. This is very boring. So here is, anyway, here's my model. I'm not sure it's the best or not. So we will talk much more about what it means to fit a model, right? Make it, optimize it to be as good as possible with your data. That means to actually minimize the loss function. That means to train the machine learning model. So we will get to this next week, actually. But for now, we're just trying to understand what the model actually is and what is happening. So that's one example of a data set. The other example here is different voting patterns. So here on the x-axis you have the income level of like American voters, for example. So here that's a one-dimensional regression. Dimensional, and so that means that D is one feature. And what you have on the y-axis, what you're predicting, the y label, in our case is how many percentage of people will vote for each party. That's another regression model you can do. You see here a linear regression will probably not do the job best possible, but it's of course still a possibility to do. Okay, that's what regression is. You're probably not very new for you, but we want to agree on the notation. And also we want to make sure we understand what is happening here, right? The model is the regression which I draw here in purple. So we will talk later about how to find a good model from a certain class or candidate set. Okay, so for now this was one-dimensional in both cases. I only had one feature in predicting my label. Of course, it's much more interesting to have a multi-dimensional regression, and that is what's happening here. So this is a dataset from advertising use case, and here they have, these are also representing people basically. So here you have actually the TV, radio and newspaper usage of a TV ad. So not exactly people, sorry. But for example, here you have the one data point here has actually three features. How do I, maybe somewhere here. So what is the data point here? So there is only one data point, xn. So n is the name of our data point, but it has three features. So xn1, xn2, and xn3. So this is our data point. So xn is, what is it? Maybe 230 and 40. So it's a three-dimensional vector. and that's our data point. And what we are going to do is we want to predict its value. It only has one value, so yn is 15, which is like how successful was this ad, which was whatever, in 200 TV impressions and so many radio impressions, so many newspaper impressions. That's one data point. Now what you want to do is to find a linear regression function, for example, or it can be anything, which predicts this yn based on the three features. So given a new data point xn, how do I predict its value y? So that's what a regression model would do in the multivariate case when there are three features, for example. Okay, so far not much new, but again I want to give this to you, that you should distinguish between prediction and interpretation. Sometimes why are we doing a regression can be to just get an accurate prediction, to be as high in the accuracy as possible for new data points. And sometimes we just care about understanding the effect if some things are actually correlated, but we do not care about the accuracy. So here you see these two examples, and that is actually an important distinction, which is very well known also in statistics, for example. This is not particular to machine learning. In both use cases, what we have to do is to find this regression function. So this is the model we're trying to find. So this is the machine learning model, is our f function. So we're trying to find or construct a good f. And this will be parameterized by something. So we will get to this. So this depends what kind of regression you want to do. For example, in a linear regression, we saw that we can have f's which are parameterized as planes. In neural networks, you can have f's which are parameterized by the weights of this neural network. So this is always what we're going to call W. So W is going to describe this f, and finding a good f to fit our input well, that's the task of training. So that's what we're going to discuss later next week when we talk about optimization and loss functions. All right, I think we are okay with multivariate regression. Nothing much new here. So just some additional notes that, if two things correlate, it doesn't mean that they are necessarily causing each other. This is super important, but also maybe not specific to the machine learning course. So here you see this nice correlation between the number of pirates in the sea and the average global temperature. So that also motivates that we should be careful with interpreting machine learning models or any statistical model. And again, you should be very clear, why are you doing this? Are you doing this to just predict when it's maybe fine? Or are you doing this to understand, to interpret? Are you claiming that there is now a causal relationship because you found that these two are linearly correlated? The terminology, maybe you've heard of different names for input and output variables. So here is a few alternatives which are well known. We will mostly in the machine learning domain, we use features. This is our input values, and we use the target or the label as our the quantity we want to predict. So the y variable. So that's an important distinction, and that finishes this part. So there's a little homework for you. If you're interested, then have a look at what's the difference between prediction and interpretation. A few examples here which make you think a bit. It's not always a hard distinction, but it's important to understand that there is a difference between the two. All right, that's all for regression fundamentals. So let's get to something a bit more useful and concrete, which is linear regression. And let me just take a 1 second break. So linear regression is assuming that there's a linear relationship between your input and output. So that's what's happening here. And let's visualize this a bit more detail. So here we have again a boring one-dimensional case. T is 1 and we have a lot of data points, so that's what all these black dots here are. And what we want to do is to fit a line. This is a bad one, and this is maybe a good one, but they are lines, so that's what linear models are. So that's what a linear regression model would aim to do. Again, here it's between height and weight of a person. So why is this interesting to do? And actually next week we'll talk about why this is the good model and the other one is the bad one. So of course this should not be this imprecise concept like good and bad, but we will aim to find a way to quantify how well the model, your linear one, fits the data. Alright, but why do we care anyway about linear regression? It's is surprisingly important, and also especially for machine learning, because so first of all, if one thing is it surprisingly works super well, especially when the data is very high dimensional. It works extremely well. So in many machine learning applications you will actually get almost state-of-the-art performance if you are using linear models the right way. There is a bit more to it than a simple linear model, but it does work well. It's very scalable to large data, and that's one reason, because it works. It's also interpretable, which is another advantage, by the way. And then the third kind of advantage is that it's really important for us to also understand the concepts of machine learning, such as underfitting and overfitting and so on. And this is something we can already observe quite precisely in linear models, and also use this to formalize these concepts. So it is an important thing, and it's surprisingly deep what can be said about it. But before we do anything deep, let's stay simple. So this I probably can do quickly because it's super easy, and you might have seen this in introductory courses already. But again, so about the terminology, it's crucial that so our model is F here. So, and this is, I want my F to be parameterized by W, so my weights. So the weights describe what kind of F I have, and then the F is a function which takes input. It takes a X here, then it maps that to F of X. What is this? It turns out F of X is this thing here, F W of X, and it's described by two things, and these two values are super simple. These are the offset term W0, and then the normal vector, as we saw previously, for example in the high dimensional case. So this thing is W1. How many units does it go up when you go 1 unit to the right? So these are the two parameters which describe the regression model here in this naive one-dimensional case. Why am I insisting on this? It's important to see the parameters are different from the data. So the data is the X and the parameters are the W. So it's very crucial. You always distinguish this because this will appear over and over again. Also, if you, for example, then go to the case of neural networks and further applications. All right, nothing special here. So let's move to the interesting case of, so this is just one-dimensional, that's why it's a bit boring. In the n-dimensional case, sorry, d-dimensional case, this will be more interesting. And that's what we call multiple linear regression or multivariate linear regression. It's the same thing. So same thing as before. Again, our F is described by parameters W. In which way? So we just need to find a way to describe all the linear models that could possibly exist. And W is used to express these guys. So that's why W is here. And if you have just D variables, then you can just have basically D Ws. Actually D plus 1 if you want to be precise here. Because, well, also here we had kind of two terms in the one-dimensional case. And we can also do this same thing in the n-dimensional case. Let me visualize this again. So, for example, if I have the weight of my person, that is my y value. I want to predict this based on some features. So the height is what we had in the previous example, and other features. So, and what I'm going to have is, again, I will have a linear model, which then means I have a hyperplane. So, well, in this case with two features, it's just a plane in 3D space. But the actually interesting thing is that if you have more than two variables, then this still works, right? You have found a way to describe any linear function by W's, namely use the W's from 1 to D to describe the orientation of this plane, and then you use the W0 is just your offset term if you want to have that. It turns out it's not even so important to have a offset term, which is kind of interesting. So in very high dimensional examples, you kind of ignore this W0 here. It doesn't really matter in practice. You don't need that. So we actually have an example for this a bit later on. So again, just to make sure that you are on the same page. So here is my data point xn. So I have D equal 2 variables in my case. And from the two features I have each data point, I will predict the target variable yn based on these two features. So I don't know, we can put any features you like. So a very stupid example would be to use gender, I don't know, so, or height. It's just, the point is that it's already very crucial how you actually represent your data as features. Features can be numerical, but it's really your job to find features which describe your data well in a meaningful way. Can be categorical or continuous features. That's your X data. So here we don't care so much how the features come to play. We just say that X features of the data point from 1 to D are available, and we want to model the class of models which we're trying to fit our data. And we do this here with the class of linear functions, and here you have all of them. So any X data point gets mapped to f of X in this way. So what has happened in the very last bit? So the most crucial thing here is that what is this inner product here? And you know this product, you know what that means, right? The X vector is transposed, so it's a row vector. It gets multiplied with the W, with the weights vector, which is a column vector, because vectors for us are always column vectors. So that's what's happening, and that's the most important operation we basically have in machine learning. It's also that's all the operations which are spent on your GPU when models are trained, and also when models are used, which is called inference. When you just have a model and you use it, that's here. We have the blue plane, we use it. So how do we get the value for input X? How do I get the value Y? I just have to do inference on my model. I have to compute f of X depending on my trained weights. So we will get to it later, how we find good W's. That's not the point here. The point here is how to describe any linear model by some W. So, and then next week we will tell you what are good W's. Okay, we need to agree on some good notations here, and one very nice thing and convenient thing to do is to write any linear plane as just one inner product of a big vector. It's a very simple trick to do that even if you want to have the offset term. And the trick is simply to just define so this x and tilde vector is you would just define it to be the all data point xn has d entries, right? But then you just add this one artificial feature to each data point, and that feature is just one for everybody. So you just put one additional feature. And why would you do that? So okay, let me actually write the full expression. So this is a very long column vector. The data point x1 goes from xn1 up to xnd, and that guy is a vector in the d+1 dimension space. So that's the same space as where our weight vector d lives. So that's kind of convenient. The space where d lives, the weights live. So why is this convenient? Because now we can just say, okay, we have one inner product we need to compute, and we are done. So okay, compute your augmented data set, and then do not worry about the offset term. That's what's happening here, and that's one side of the story. And of course, this is actually, it sounds a bit like a technicality. It is, because as I told you, it doesn't really matter so much in reality if you use an offset term or not. But still, mathematically, it's important. And it's also important to then train the models. It's not clear which models are easier to train, right? If you can find the best W's with an offset or without an offset, that might not be so trivial. But that's here just for convenience. Here it seems that we can describe any plane in this simple way. We do not need offset terms because any linear model with an offset is equivalent to a linear model on data without an offset term, where you just add one fake feature to each data point. So that's the augmented data set, and that's a very useful trick and gives you a bit of a feeling of what is happening in such large high-dimensional models, and also what's happening if you implement this in Python. You can already implement this, so if somebody gives you weights w, then you can easily implement this to get the answer for any input x. You can spit out the answer fw of x. The notation is important here because always the model will be parameterized by some w, no matter if it's a real neural network or if it's just a linear regression as here. That's something to remember. And with that, I think we have a good point to stop for a second, and see you on the second video, where we're gonna finish this regression part and then move over to defining loss functions to find the best fit of machine learning models, to find the best fit to the data, and which is the training process actually. Okay, see you in the next video. Thanks for staying on.